You guys ever encountered this problem out in the wild? You see a monkey chilling on a ladder, and the ladder is held between two frictionless surfaces, the floor and the wall. And at the bottom, a rope is holding the bottom edge of the ladder, but the rope is frayed, so it's about to break after being exerted with more than 80 newtons of force. And you've asked yourself, can I analyze this scenario using classical mechanics that I've learned in class? Today we're going to do this. So if you encounter this scenario with a monkey on a frictionless surface on a ladder with a rope that is fraying, you are going to have no problem with analyzing the scenario, and you can tell the monkey, hey, do not go higher because the rope is going to rip and you're going to get hurt. I'm not going to read the problem. I'm just going to dive right into it because I'm probably going to read the problem 64 times before we end the video. But I'm going to try to do it fast because, as you guys have seen with my videos, they end up being very long. We're going to try to solve it today, so I'm not wasting your guys' time. Let's read the problem, and let's start with part A, which is right over here. It says draw a force diagram for the ladder. All right, force diagram. Here's the ladder, right? The center of mass is important. The center of mass tells you the weight of the ladder. And this weight is a force. Force, I'm going to do ladder right here. Force is equal to mass times acceleration, Newton's second law. In this case, acceleration is due to gravity, and the mass of the ladder is actually given to us, but I'm going to just write mass of ladder times g. So force is equal to mg, the mass of the ladder, which is given to us, and g is 9.81 meters per second squared. This gives us a force in newtons. Awesome. What else is happening? Well, there is another force. Right here is the wall, and the wall is pushing against the ladder, right? If you push against the wall is pushing against you. This is Newton's third law. Every action has an equal and opposite reaction. The ladder is pushing against the wall, so the wall is pushing against the ladder. I'm going to call this F wall. We don't really know what this is, do we? We don't. And on the bottom side, we have the rope. The rope is pulling the ladder, right? So I'm going to call this F rope. And there's another thing, the monkey. Does the monkey rest at a specific... Oh, actually, they say the weight of the ladder is 1.2 times 10 to the 2 newtons. So this is actually given to us in newtons already. There's a difference between mass and weight. The monkey, actually, they give us the mass in kilograms. The length of the ladder is 3. The ladder rests on a wall, makes an angle of 60 degrees. The upper and lower ends of the ladder rest on a frictionless surface. The lower end is connected to a wall by a horizontal rope that is frayed and can support a maximum boom. Okay, so that's it. Actually, if we know the where the monkey is, right? Let's say the monkey is chilling like over here, then the monkey is also pushing the ladder down with a force of monkey, which is again mass of monk times gravity. This is the free body diagram. You have to write this out, and that solves problem 2 or part A. So I'm gonna cross this out. Actually, let me cross it out a little bit like that so it's visible. Actually, let me use red so it's more visible. Draw a force diagram on the ladder. Boom, done. B, find the normal force exerted on the bottom of the ladder. Oh shit, I forgot a force. Yes, there's a normal force right here. The ladder is being pushed up against the ground, and the ground is pushing up against it. And normally this is called the normal force. Norm. Why is it called the normal force? If I'm sitting in a chair, the chair is pushing up against me. This is seen everywhere. If you have a bottle chilling on a desk like this, the table is pushing up on the bottle with the same amount that the bottle is pushing down on the table. This is called the normal force because the force is normal. Normal is another word for perpendicular. So this is why you use the word normal in this scenario. Now A is done. Sorry about that, little mistake. Find the normal force exerted on the bottom of the ladder. How do we find the normal force? There is a conservation of forces here, right? The sum of forces has to equal 0 because this scenario is in equilibrium. The chapter here is called equilibrium or static equilibrium or something like this. This is from chapter 12 of Serway and Jewett, Physics for Scientists and Engineers. But I could be wrong. If I'm wrong, I'm going to put the chapter up here. If I'm not wrong, I'm still going to put the chapter over here because it looks cool. Respect, Serway and Jewett. Thank you, guys. So how do we find this force? Well, take a look at this. How many forces do we have acting in the y direction? Right? We have to look at the forces acting in the y direction. In the x direction, there's only these two forces. They're in equilibrium. But in the y direction, we have these two. right? So what's going to happen is there's going to be forces pushing down. These guys are exactly equal and opposite to forces pushing up. Equal and opposite because if I take this force, move it to the other side, it gives me down minus forces going up, and this equals 0. This equation here is super important. This is what equilibrium means in an equation form. I like this version, but a lot of people use this version here because you can see the 0, and 0 is pretty cool. Anyway, this is equilibrium. So I'm going to use this, but actually let me save some room here, and maybe this is going to be useful for you guys. So I'm going to just put this boom right here, and I'm going to solve part B right here. So we have F norm is equal to, the forces going down is F ladder, I'm going to just do F lad, plus F monk. Now you can write this on your exam. You might not get great marks, but this is the starting ground, okay? You're going to get part marks if you put this, but you want to express it in actual forces. Find the normal force. A force is a number with the units of newtons right after it. So we have to find this. We can't just put this equation. So this means we're going to have to start doing some algebra. Force norm. This is what we have to find. Let's put brackets. Find the force of the ladder. What is the force of the ladder? Here we say a uniform ladder with a weight of this many newtons. Weight is a type of force. It is a force due to gravity pulling your mass down to earth. And it's already in newtons, so we're going to go 1.20 times 10 to the 2 newtons. If you wanted to find how much this ladder weighs, like how much mass this ladder has, you can just use F equals mg. You have the force, you're looking for m, and you have g, it's 9.81 meters per second squared. Divide the g out on the other side, cancel some units, and you're going to get mass in terms of kilograms there. Cool. Alright, that's it. Now we move on to the force of the monkey. The monkey is actually given in 10.0 kilograms, and this has to be multiplied by 9.81 meters per second squared. Cool. So in the first term here, we don't have to simplify anything because our final answer has to be in newtons. But in the second term here, I'm actually going to use my calculator here. Actually, we don't need to use a calculator. It's 10 times 9.81. You just move it the decimal place. It's 98.1. And then here we have kilogram times meters all per second squared. You guys see what I'm doing with the units? I'm taking this unit, combining it in the numerator because they're in the numerator. The only thing in the denominator is second squared. I'm going to give you guys a 1 million IQ trick here. Remember F equals ma? You cannot forget this. This is Newton's second law. What does F have units of? It has units of newtons, and m is mass. This has units of kilograms. And what does acceleration? Acceleration is meters per second squared. So if you ever forget what newtons means, just remember F equals ma, and you're going to see that newtons written out in SI units is kilogram meters per second squared, which is exactly the units we see here for the force of the monkey. So we can actually convert this entire thing over here to newtons, all right? And now we can combine these two things together. I don't really like scientific notation, so I'm going to just multiply this by 100, which gives me 120 newtons. Right, plus 98.1 newtons, and this gives me, let's see, 198 plus 20 is going to be 228.1. Is that true, or am I tripping? Yeah. Right? No. There's a 1 here. Because 9 plus 2 is 11. Carry the 1, it goes to the 2, and then the 8. Okay, so this is the final answer for B. Alright, we're going to check if B is actually correct. I think I found the solutions to this problem, but I'm not too sure. And I'm hopping in this problem with no background theory. I'm just talking to you guys like about what I think here. So find the normal force exerted on the bottom of the ladder. We found it 218.1 newtons. I think an apple is about 1 newton, so a ladder with a monkey on it, 218 apples, like, I don't know. Try to make sense of this. I guess it looks good to me. I mean, the ladder is 120 newtons and the monkey itself is 98 newtons. Normally a ladder should be heavier than a monkey, but I haven't held a monkey. I've held a ladder and it's kind of heavy, but they're made of aluminum. They should be pretty light because you're going to lug the shit around. So anyway, I guess this makes sense. Ladder is a bit less than a monkey. Or monkey is a bit less than a ladder. Okay, C, find the tension in the rope when the monkey is 2/3 of the way up the ladder. This is some crazy shit, guys, because this is where we're gonna have to use the length of the ladder, the angle 60 degrees, and we're gonna have to see what was going on here. So let's draw a picture. Right, we have the ladder here. Let me actually use this white. This is part C. And we have the force of the ladder, which is 120 newtons. Right, we have the force, and what are we looking for? Find the tension in the rope when the monkey is 2/3 the way up the ladder. Ooh, this is gonna be tough. This is gonna be tough. Here we have F wall, right? Here we have F rope. F rope is what we're looking for. And 2/3, if you cut the ladder up into thirds like this, so this is 1/3, this is 2/3, and this is 3/3, the monkey is chilling exactly right here. So the monkey is activating it's imposing its 98.1 newtons right here at this third here. I'm gonna erase all these thirds. Boom. And then we also have the normal force, which is pointing up. And we actually found the normal force, didn't we? 218.1 newtons. If we got the normal force wrong and we have to use the normal force in our calculation, our error is going to progress through the problem. So this is going to be ass. But if we didn't make a mistake, we're going to be good. However, if you make a mistake on a final like this, just keep pushing through. It doesn't matter. Even if you can't find the answer, just say, I'm guessing the answer is this, and move on with the problem and try to just do better on part B, C, D, whatever. Anyway, we're going to keep zooming. Find the tension in the rope when the monkey is 2/3 up the ladder. So how do we find the tension in the rope? The tension in the rope is literally F rope. How do we find this? Well, Newton's third law says every action has an equal and opposite reaction, and this system is in equilibrium. So it seems like it's literally going to be equal to F wall. Now, how do we find F wall? This is going to be a tough one. I actually have no clue. I have no clue. So I'm going to have to think about this. And while I'm thinking, I'm just going to read the rest of the problem. I'm imagining like I'm doing this on an exam. I've already wasted 13 minutes just yapping. So let's read part D and just keep thinking in the back of the head about part C. Part D says, find the maximum distance D that the monkey can climb up the ladder before the rope breaks. Okay, so I think this is connected because it says the maximum tension of the rope is 80. And if we figure out the tension of the rope when the monkey is 2/3, then we can kind of use the same procedure in C to find part D, because we'll just find where, like at what point of the ladder the monkey hits where the tension on the rope exceeds 80, and then we're going to say there is where the monkey can go, the distance here. But we don't know how to do C, so now we don't know how to do D either. But I'm just going to keep thinking and keep going to part E. If the horizontal surface were rough and the rope were removed, how would your analysis of the problem change? What information would you need to answer parts C and D? And so part C, D, and E, we cannot answer unless we think. So let's think. You're at a final exam, you're just thinking. At this stage, if I'm on a final exam and I don't know how to do this, I'm just going to go to the next problem. Maybe if I have an idea, I'm going to just write something here. So maybe like, does torque have something to do with it? Does the angle 60 degrees and the length of the ladder have something to do with it? That's all I can think of. So I wrote some little guesses, some little trials that I could try out. Then I'm gonna go to the next problem. But since I don't have an exam, maybe I'm just gonna chat with you guys while I think. How you guys doing? Semester is going well. This is good. You know, you guys gotta make sure the stress levels are not high. What do you guys think about this problem? Is there a way to solve it? So we need to find the force on the wall. The wall is pushing against the ladder. The ladder is being pulled down. Hold up. The ladder is being pulled down, okay? It's being pulled down by the monkey and the mass of the ladder. It's being pushed up a little bit too by the floor and is being pulled this way by the rope. Okay, I'm gonna start cooking right now. Wait, can I even cook, bro? No, I can't. What am I looking for, bro? I need to use 60. I need to use the angle 60 degrees somehow because I'm trying to think if the equations in the horizontal direction have some kind of information in the vertical direction, right? Like the first problem, we did something related to the vertical direction, right? We found the normal force using the force of the monkey and the force of the ladder, and the conservation of forces in a static equilibrium system. But in the horizontal direction, we have two unknowns, the F of the wall and the F of the rope. So some information has to be included in the vertical directions, otherwise we're fucked because we can't do anything. Like we can't just find F of rope with F of wall. You see what I'm saying? So we have to do something here. We have to do something. And what is it that we can do? I'm gonna just read the problem again. 15 minutes spent on one problem. Okay. All right, let's see here. 10-kilogram monkey climbs up a uniform ladder with a weight of 1.2 times 10 to the 2 newtons. The ladder has a length of 3. The ladder has a length of 3. Okay. So I'm gonna try using something like this. I'm not gonna talk about torque because I'm not really comfortable with torque yet. So I'm gonna draw a separate picture right here. The ladder is like this, right? The wall is like that, and the ground is like this. Then we have, let's do it in red, 60 degrees. And about 2/3 up is the monkey. The monkey is booling here, and the mass of the ladder is at the center of mass, which is right in the middle. So if the ladder is 3 meters, wait, is it 3 meters? Yeah. Then half of it is going to be 1.5 meters, and 2/3 of it is going to be 2 meters. What does this tell me? Does this tell me anything, guys? I'm thinking here, I'm thinking. Okay, well, I know that here we have 90 degrees, and I know that a triangle adds up to 180 degrees. So we have 90 degrees plus 60 degrees. So this unknown angle here has to be 30 degrees, right? Because 90 plus 60 is 150 plus 30. All right, so we have 30 degrees here. Does that help us in any way? Sine and cosine. Sine and cosine are going to be useful here, huh? Normally final exams are 3 hours. I've spent 20 minutes on this single problem. And maybe I've read some of the other problems. Maybe I've solved some multiple choice. But okay. Oh. No. It doesn't work. Wait a second. We have one equation and two unknowns. If we have two unknowns, we need two equations. Two equations, two unknowns, you can solve this. But one equation, two unknowns doesn't work. So we need two equations. And where do we get the two equations from? The theta. Okay, guys, I'm trying to think here. I'm trying to think because what I think we can use is like sine of theta equals opposite over hypotenuse, right? Sine of theta. If we take sine of 60 degrees, then the opposite of sine is going to be, and let's talk about forces here. Let's talk about forces. The opposite of sine is going to be this. What is the opposite? Bro, I don't think this is going to work. Sines and cosines here. Okay, let's look at the picture here, right? This angle is 60 degrees, right? So this force and this force. Right, if you bring this force here, okay. Okay, look at this, bro. Hold up. Is this simple? Is this simple? Look at this, guys. We have the normal force right here, right? the normal force, which we actually found, F normal is equal to 100, hold on, what was it? 218.1 newtons. This is the force from B. Find the normal force exerted on the bottom of the ladder. Okay, 218.1 newtons. Boom. Now check this out. What we're looking for is the force of the rope, right? No, this doesn't make sense. Because it says the monkey is 2/3. Find the normal force exerted on the bottom of the ladder. Find the tension on the rope, and the monkey is 2/3 up the way of the ladder. This doesn't make sense. The monkey climbs up a uniform ladder. The ladder rests against the wall. The 2/3 is fucking with me. Because if the 2/3 wasn't true, check out what we have here. Check out what we have here. We basically have a triangle where this is the ladder, right? Then over here we have the force vector, which is F rope. And then we do have this guy here, which is F normal. But if you translate this guy at the end of this one, this is completely okay to do. And you take a look at this angle here, this angle is 60 degrees. So what we could do is opposite over hypotenuse, nah. Cosine is SOHCAHTOA, opposite over adjacent. We need tangent here. We have tangent of theta is equal to opposite over adjacent, which in this case is going to be F norm over F rope. We have F norm and we're looking for F rope, and we have theta, and we can use tangent in our calculator. So this equation right here has only one unknown, and the single unknown is F of rope, which is what we're looking for. So this is a way of doing this problem. However, what is fucking us is the 2/3, because the 2/3 isn't used anywhere here. You guys see what I'm saying? The monkey climbs up over here, boom, he puts his weight here. So perhaps, because look, if the monkey is chilling here and the monkey's mass is pushing down, this F norm is going to change, right? And if the monkey climbs up a little bit, he is putting his weight here, right? And some of the weight is going here, which is changing the F norm, but also some of the weight is going up the ladder and pushing against the wall, which is then creating this F wall to increase. So depending on where the monkey goes up the ladder, if the monkey is sitting right here, almost all of his force is pushing down the ladder, which is then pushing on the wall. So a lot of the monkey's mass is gonna, or a lot of the monkey's force is gonna be included in this F wall over here. So if the monkey is 2/3 of the way up, then F norm is not gonna be this, because before what I calculated F norm to be, well, I just thought the monkey was like right in the middle, no? You know what, guys? If I'm on the exam here and I didn't know what to do and I'm stressing for time, I would literally do this, boom, and I'm actually going to do that right now and see if I get it wrong. So we have tangent of 60 degrees is equal to F norm, which we said was 218 point. No, it's not going to work, because the next problem is going to ask us, where does the monkey go? And if this does not work, then we can't do the other problem. But I'm still going to write this, F rope. So then F rope is equal to 218.1 newtons over tangent of 60 degrees. All right? I'm just going to peep what tangent of 60 degrees is real quick. Tan 60 degrees. 1.7. Maybe this makes sense. 1.73. So 2.18. 218.1 newtons divided by 1.732. Let's do 732. Notice that tangent of 60 is a unitless number, and the only units that are left in this calculation are newtons. So now let's do 218.1 divided by 1.732 This gives us 125. This is not good. 125.92 newtons. So this is the force of the rope, and the rope is already broken. And we didn't even include any information where the monkey is chilling. Okay, but check out what I'm doing here, guys. I was just thinking, and I got some push through. I got some like engagement in the problem here. I'm still thinking, and I've wasted 30 minutes of the exam time on one question. So you gotta think quick here, and this is why you gotta do a lot of these problems to check out like what the fuck is happening. Because I haven't done this problem before, and I'm just going off the dome here with Newton's law and some conservation stuff I remember from the past. But you know, I know that it's wrong. Find the tension in the rope, and the monkey is 2/3 of the way up the ladder. 2/3 of the way up the ladder. The monkey is pushing down. Boom, and then the ladder. How can we say what the monkey is doing? 2/3 of the way up the ladder. I think I got it. Peep this. Well, it's going to be another sine cosine tangent thing. Okay, the ladder is like this. This is 1/3. This is 2/3. Boom. Monkey is here. The monkey is pushing down. Now peep this. Right. This is the floor. Boom. And this is the wall. Boom. And what we have over here is, you got to take a look at the degrees. You got to be good with angles here. This is 60. This is 90. This is 30 degrees. If the wall is like this and the ladder is like this, then this should also be 30 degrees, right? You guys see what I'm saying? So you have this angle here. You just slide this angle. Boom. There's another it's parallel lines, cross section. This angle is literally the same shit right here. Boom, 30 degrees. So let me write 30 degrees. Now, what I'm trying to do is find where the mass of the monkey is going to go, because, peep this. The mass of the monkey, bro. The mass of the monkey is 2/3 of the way up. This is 2 meters. Okay, the triangle is being pieced together right now. We have 2 meters. We have the force of the monkey, which I should write right here. Force monkey mode. Force of the monkey is being pushed down. We can use the 2 meters, but can we? Can we really use the 2 meters? We can't, bro. We can't. The triangle has to have the same units everywhere. Otherwise it ain't gonna work. But maybe we can do another sliding vector thing like we did before. So here's one part of the vector. We have the force of the monkey, and it's 2/3 up, 2/3, right? And there's this angle 30. And maybe we can find another force vector here, huh? How much force is being pushed this way? So if the monkey is pushing down here, then there's some of the force is going this way. I'm assuming that's this, right? Because this is the part of of the thing here. And some of the force is also going here. But how much? How much? So this is the force that's going into the rope, maybe. And this is the force that's going into the wall. I'm just thinking how we can include information about the monkey. It's gonna have to, look, this equation here is good. We're just gonna have to somehow change the normal force. And the normal force is up here, huh? The normal force is up here. So how do we include information on the monkey inside the normal force? The normal force has to change. The monkey's weight is always pushing down. 30 minutes exactly on this problem. Oh my god, I need to think. I need to just dissociate and think about this problem. Just visualizing what a monkey on a ladder would look like in real life. And like, if the monkey goes further up the ladder, what happens physically? Like, I can imagine this, you know what I mean? It's a monkey on a ladder, like you see this every day. I'm trying to think about this. In the summertime, I was helping my dad with a ladder, and like I was holding the ladder so the dude wouldn't slip, because this is like frictionless, you know? And at the bottom, I don't need to hold it that much because my dad's weight is like right there on the first rung of the ladder. Like right here. Boom. But as he's climbing up, like right here, if he's right here, I have to hold the ladder a lot because for some reason, if he's right here, like there's a big chance of the ladder slipping out. So the higher you go up, the more force you put onto this rope over here. The more force you put on the person holding the thing back over there. If it's frictionless, you know. If it's like rocks and shit, you could just, you know, friction's gonna hold it together. But man, I'm thinking, bro, there's definitely a way to connect this here. And I'm imagining myself at a final exam. I don't want to check the solutions right now. I want to do this with you guys as if we were at the final exam together. But I'm caving, bro. I'm caving here. I don't know. Should I check a solution? Check to see like how to do this, or should I just keep grinding? I'm gonna try to do this no cuts so you guys can see like my process of thinking through this shit. Man, but it's tough. Like there has to be something to do with the 2 meters because the ladder's length is given. It tells us 2/3 of the ladder up, and 2/3 of a 3-meter ladder is 2 meters, and the angle there is 30. Basically, we have a triangle. Here we have 2 meters, and this one is the force of the monkey, which we actually know, right? Force of the monkey is 98.1. 98.1 newtons. But we can't do this because these units don't work. If we have an angle here, theta, which is 30 degrees, we have adjacent over hypotenuse, which is cosine. Cosine is going to be 98.1 newtons over 2 meters. No, it's not going to work. We can't use 2 meters. I mean, we should. Alright guys, I think I'm actually going to check a solution. I am sorry. Bruh, we gotta use fucking torque, guys. We gotta use torque. But anyway, I checked quickly this. I got the solution manual from Serway and Griffith, or Serway and Jewett. We got this. This is correct. They say 218 without the 0.1. So 218, this is correct. But here they say like, oh, the pivot point here, boom, and then this. Oh man, torque, bro. This is why I told you guys earlier. Man, I didn't study torque. I should have studied torque. All right, so what are they saying? Here's the ladder, right? This is the pivot point. The monkey is 1/2 of the way up, 2 meters. Man, this makes so much sense now that you actually think about it, because torque has fucking distance in it. What is the equation for torque? It's torque, which is actually a vector, is equal to, I didn't check the full solution. I just saw they used torque, and then I was like, okay, I'm not going to look at this anymore. I'm going to try to work through it. This is R cross F, right? Or if you want to get rid of the cross product, you could just do magnitude of R times magnitude of F times sine theta of the angle between them. So in this case, we have here F of monk, which is 98.1 newtons, which is already a force. That's fantastic. And then here we have the distance, right? This R is just straight up 2 meters, right? 2 meters, and here's the angle between them, bro. Oh my goodness, we were so close, guys. Here's the angle between them. It was 30, huh? 30 degrees. So let's find the torque. I mean, how does the torque even help us? Do we do torque conservation or something like this? Okay, so we have 2 meters times 98.1 newtons times sine of 30. I think sine of 30 is 0.5. That's peep. Sine of 30 degrees. Yeah, 0.5. And then let me do 0.5 times 2, which is just 1, times 98.1. It's just 98.1, bro. Spread them on. 98.1 Newton meters. Now, how do we use this actually? Crazy problem. I would not have thought of doing this. Sum of torques, right? There's several torques going on over here. So we have sum of torques equals 0. So we saw that 98.1 Newton meters. This is the torque of the monkey. Then we have the torque of the ladder, which is 1 meter times 120 newtons times, I should probably shrink this, huh? the ladder has a torque, right? The ladder is up here. This is its R. It's pulling down. The thing is, they used a different angle in their torque, which is kind of scaring me. But I'm gonna keep doing it my way. So the ladder, 1.5 meters, huh? The ladder is 1.5 meters. 1.5 meters. And then here you have sine of the angle between them. And it should also be 0.5, because sine of 30 degrees is 0.5. And then you also, I guess, have this and this guy. And the force of the wall. Whoops. So here's the final torque. 3 meters times force of wall. Okay, I guess this force of wall is going to help us. Times sine of the angle between the force of the wall. So this is force of wall. What is this angle? Boom. Is it going to be the same as this angle? Yeah, this is 60. Sine of 60. Yeah, I think this makes sense. Okay. Let's plug this all in. Pull up a calculator real quick. So 1.5 times 120 times 0.5. This is, we have 98.1 plus 90 plus sine of 60 degrees gives me 0.886. That times 3 gives me 2.598 force of wall. And all of this equals 0 because of conservation of torque. God damn, bro. Conservation of torque is important. Now we have 98.1 torque of the monkey. Hold up, backspace. How do I have backspace here? Brother, there's no backspace on this cal. Oh, there is. Plus 90, the torque of the ladder, equals 188. So basically we have 2.598. This is meters actually, because sine of 60, this is meters, and then force of wall. And then on the other side we have, subtract all that, we have minus 188.1 Newton meters, right? And then if we want to divide this 2.598 meters, 2.598 meters. Here we have the meters and meters cancel, meters. So we have F wall is equal to negative force. Oh, I guess that makes sense because it's pushing the other way out. So 1.188.1 divided by 2.598. So F wall is equal to 72.4 newtons. Negative actually. And then we can go back to our original thing. So we found this, and that equals exactly that. Except negative. So let me peep. So F rope is equal to, is it negative or positive? I guess they're pointing in opposite directions. Let me just say 72.4 newtons. Let me check if this is correct. 72.4. Okay, this is correct. Okay, guys, sorry about that. I fucking did that in 43 minutes with a solution manual. I hope you guys learn from this and don't make the same mistake in the exam. Let's try to do, this was part C, right? Let's try to do part, so part C was done. I'm gonna do a blue cross there because we did it with a freaking solution manual. Find the maximum distance D that the monkey can climb up the ladder before the rope breaks. Okay. So what we did here, and actually we're going to use what we did here quite a lot. So what we did was a sum of torques equals 0 because the system is in equilibrium. This is the sum of the torque created by the monkey. This is the sum of the torque. This is just the torque of the ladder. And then this is the torque of the wall. So technically, here, this F wall, this thing went inside here, right? And then all of this added up to give you 0. So everything we have here is good, except now the torque of the monkey is going to be our unknown because we want to figure out where the monkey is in the ladder. This thing is going to be locked in because remember they said here in the beginning 80 newtons is the maximum tension that the rope can hold. So what we're going to say here, and by the way, this tension is lower than 80, so the monkey at 2/3 of the ladder is not ripping the rope. Now we're going to say F rope, so this is for the final part, F rope is exactly equal to 80.0 newtons. Therefore, F wall is equal to minus 80.0 newtons. Then we can basically create our torque equation again. So we have 0 equals, let's do the torque of the monkey. The torque of the monkey is R, which we don't know, times the force of the monkey, which is 98.1 newtons, times sine of 30, which was 0.5. 0.5. So this R is what we're looking for here. Actually, I'm gonna do X. X is going to be the length of the ladder that the monkey can go. And at exactly that length, we're gonna hit 80 newtons on the rope. And then just a little bit beyond that, it's gonna break. So it has to be above 2/3 of the ladder, but it obviously has to be before the 3 meters of the ladder. Then the next thing looks good. So plus 90 Newton meters. This is the torque of the ladder. And then we have F wall. So 3 meters times, this is negative 80 newtons times sine of 60 degrees. So everything here is known. We'll pull up the equation here. So let's do 98.1 times 0.5. So we have 0 is equal to 98.1 times 0.5. So we have 49.05 times x. X is the thing we're looking for. Just underline that in red. Then we have plus 90 Newton meters plus, actually this is going to be a minus, it's going to be a negative because we have a negative value in there. So we have 3 meters times 80, I pulled the minus sign out, times sine of 60 degrees inside that bad boy. Oh, we have minus 207.846. And this is Newton meters. The units are important. Okay, I'm going to move the 207 on the other side. It becomes positive 207, but we have 207 minus now 90. So on the other side of the equation, what we have is 117.846 Newton meters. That equals to 49.05 times x. I'm going to just put x on its own and divide 49.05. And what were the units of 49.05? It was just 98.1 times 0.5. So this is newtons. So now we have a good cancellation of newtons and we just have meters left over, which is exactly what we're looking for here. So 117.846 divided by 49.05. This gives us 2.40 whatever meters, which is less than 3 meters. So at exactly this location up the ladder, we're gonna hit 80 newtons, and if the monkey even hits that, the rope is gonna break. Or if it goes just 1 millimeter above that, the rope is gonna break. So this is part D. Let's just check quickly, find the maximum distance. Okay, let me check if the answer is correct for this. Hold it down. My phone is low battery. Wait a second, I lost this picture. So 2.41 meters. They round up a little bit? Okay, fine. 2.41. meters. Okay, nice. So what we did here was use combination of torque in a ladder problem, very important, but also Newton's second law, very important. Equilibrium, also very important. Now let's kind of philosophically answer. Actually, I'm going to do this. Boom. If the horizontal surface were rough and the rope were removed, how would your analysis of the problem change? What other information would you need for your answers in parts C and D? If the horizontal surface were rough, friction is included. Now you have the force of friction, which is equal to the friction constant times the normal force acting on that. So if you have something like I don't know, if you have like a mouse on a very rough surface, you need the weight of the mouse and you also need the coefficient of friction on this surface and the mouse. And this will give you the force of friction, which is acting opposite to what's happening. So it's kind of replacing the force of the rope. What other information would you need? You would need the coefficient of friction, and I think that's about it for your answers in part C and D. I think that's it. Let me check the answers here. It says, if the horizontal surface were rough and the rope were removed, a horizontal static friction force directed toward the wall would act at the bottom of the end of the ladder. Otherwise, your analysis would be much as what is done above. The maximum distance the monkey could climb would correspond to the condition that the friction force have its maximum value, mu s times normal force. So you would need to know the coefficient of static friction between the ladder and the floor to solve part D. Amazing. Guys, thank you for watching. 51 minutes. This is literally like 1/3 of your exam for one problem, and you don't have the solution, so you have to study for this. Do as many problems as you can. Let me know if you want to see another problem, and I'll try to rip it out. And remember, study the torque chapter. The torque chapter is what fucked me up today. Don't let it fuck you up on the exam. Thank you guys for watching. Peace out.